Hello students, welcome to the class of complex analysis. So today our topic is argument principle. So before stating the principle, I want to define what is a meromorphic function. Meromorphic functions. So a function is said to be meromorphic if it is analytic in a region except at poles for that function. That means if G is an open set, G is open and f is a function defined and analytic, f is a function defined and analytic in G except for poles. So which kind of functions are called a meromorphic function? So meromorphic functions are analytic except at poles. So I can say that poles are the only singular points of that function. That means f cannot have essential singularity or removable singularity. The only singularity is pole. Okay. For example, if you consider the function 1 by z, then you see that z equal to 0 is a pole. Therefore, this function is a meromorphic function. This function cannot have no other singular points, right? So, which implies it is meromorphic in C. Meromorphic in C. Complex plane. And I can say that every analytic functions are meromorphic functions. Another example is every analytic function have no singularities. So since it has no singularities, we can say that it is trivially a meromorphic function. So every analytic function is meromorphic. Then you consider any rational function. It is of the form some 1 by some fz divided by gz, and you can see that this function is not analytic at the points where g is 0. So zeros of gz are the poles of, then I can say zeros of gz are the poles of function fz. Rational function f by g are the poles of f by g. Therefore, it is a meromorphic function. So, these are some examples of meromorphic functions. Okay. Now, we will state what is an argument principle. Okay, the argument principle says that let f be a meromorphic function defined in a region G. Suppose we have a region G and f is a function which is meromorphic. That means the singularities are poles, meromorphic function. And we have given that this function has zeros, z1, z2, etc. zn are the zeros of function. That means f of z1 equal to 0, f of z2 equal to 0, etc. f of zi equal to 0 for every I equal to 1, 2, 3, etc. n. Okay, and p1, p2, etc. pm are the poles of the function. That means f has, or I can say that z equal to pi is a pole. It's a pole of fz. Okay, so these are the two conditions given, and which is these poles and zeros are counted according to its multiplicity. And if we consider any gamma, which is a simple closed rectifiable curve in G with the gamma is homologous to 0, then we consider a closed curve gamma, okay, and which does not passes through any of these zeros and any of these poles. Okay, then 1 by 2 pi I integral over gamma f dash z divided by fz dz will be defined by, or will be equal to sum of index of each zero minus sum of index of each pole. Okay, so which is the definition? That means the integral of the form f dash z divided by fz over a curve gamma, which this gamma does not passes through any of the zeros of fz, and poles of f z, then this kind of integral can be evaluated by using the index number, the winding number with respect to every zeros and every poles. Then sum of zeros minus sum of poles will be the given value for the required value for the integral. Okay, now we will consider the proof. Okay, now if z equal to a, consider a 0 of f z, then what can we say about the f dash z by f z? So if z equal to a is a 0 of f of order m, then which means that z minus a raised to m is a factor, right? Is a factor of fz. Therefore fz can be written z minus a raised to m into some gz, right? Where g of a is non-zero and g is analytic. So when we have a 0 of order m, then fz can be written z minus a raised to m into some gz, where g of a is non-zero and g is an analytic function. Okay. When fz is equal to this product, what will be f dash z? F dash z will be equal to differentiation by product rule. First function z minus a raised to m, derivative of second function is g dash z, plus second function is gz, derivative of first function, that is m into z minus a raised to m minus 1. Okay, then what will be f dash z divided by fz? Because we want to evaluate this kind of integral, right? So what will happen, this in ratio when z equal to a is a 0 of the function, then f dash z divided by fz can be written, we can divide each term by fz. And what is fz? Fz is equal to f dash z divided by z minus a raised to m gz, that is fz. So which is equal to, when you divide each term of this sum by z minus a raised to m into gz, it is of the form g dash z divided by gz, right, plus m into m divided by z minus a. So this will be the format of f dash z by fz, that is f dash z divided by fz can be written m divided by z minus a plus g dash z divided by gz. Okay, and we have g of a is non-zero, because a is a 0 of fz, g of a is non-zero. Since g of a is non-zero and g is analytic, right, and g is analytic, we know that every analytic function is continuous. So which means g is continuous and non-zero at a. G is continuous and non-zero. G of a is non-zero means function g has non-zero value at the point a. So when a continuous function is non-zero at some point a, then that function have to be non-zero for some neighborhood of a. Then g is continuous. Then g is non-zero. Then g is non-zero for a neighborhood of a. Okay, so which means that since g is non-zero for a neighborhood of a, means g dash z divided by gz will be analytic in some neighborhood of a, which means that g dash z divided by gz is analytic because the denominator is non-zero for the points near to a. Therefore g dash z by gz is analytic for the point z which is near to a, right? G dash by gz is analytic in some neighborhood of a. Okay, now, and this is a fact for z equal to a is a 0 of the function f with the order m. Now what will happen to this quotient f dash z by fz when z equal to a is a pole of f? So let z equal to be a pole of order m for the function f for fz. Then by definition z equal to b is a pole means then there exists an analytic function analytic function g set such that f set can be written g set divided by z minus b raised to m. So when denominator have the term z minus b raised to m, then z equal to b will be a pole of order m for the function f z, because zeros of denominator are the poles or singularities. Okay, and I can say that g at the point b is non-zero and g of b is non-zero. Okay, therefore f z can be written g z into z minus b raised to m, right? Then you find out f dash z. Then what will happen? First function into derivative of second function, that is m into z minus b raised to m minus 1, plus second function into derivative of, this is minus m. So this will be minus 1 minus m. So z raised to minus z minus b raised to minus m g dash of z. Then f dash z divided by f z will be, the first term was minus m z minus b raised to minus m minus 1 whole divided by into gz whole divided by fz. What is fz? Z minus b raised to minus m gz. Okay, plus the second term was z minus b raised to minus m g dash z, and it is divided by z minus b raised to minus m gz. Okay, then this can be cancelled, this is also can be cancelled. So what you get the value, gz can be cancelled, there is some 1. So minus m divided by z minus b plus g dash z divided by gz. This is f dash z by fz. Okay, again we have g is analytic, and g dash of, and g of g of b is non-zero. So when g is analytic and g of b is non-zero means g is continuous and g of b is non-zero. When a function is non-zero at some point and which is continuous means there is a neighborhood at which the function should be non-zero for every point in that neighborhood, which means g is non-zero for every points in some neighborhood of b. So which implies g dash z divided by gz is analytic in some neighborhood of b, in the same neighborhood of b. Okay, so we got this. Now we will use these two ideas. When z equal to a is a pole, f dash z by fz is of the form m divided by z minus a plus some g dash z by gz, and when z equal to b is a pole, then f dash z by fz can be written minus m divided by z minus b plus g dash z by gz, where g is an analytic function and g of z is non-zero. So now we have from the statement of argument principle. Now let z1, we have z1, z2 etc. zn be the zeros of fz, and p1, p2 etc. pm be the poles of fz. Then by these two statements, fz can be written z minus z1, z minus z2 etc. z minus zn, because these are the zeros means they are the factors, right? z1 is a zero means z minus z1 is a factor, z2 is a zero means z minus z2 is a factor, so they can be considered as a product of these factors. And we have p1 is a pole. When p1 is a pole, z minus p1 raised to minus 1, or I can write whole divided by z minus p1 is a pole, therefore it must be in the denominator. Then p2 is a pole means z minus p2 is a factor in the denominator, term in the denominator, etc. etc. z minus pm is a pole, and product some gz. Okay, where gz is analytic and gz is not equal to 0. at which for any set equal to z1 z2 etc and p1 p2 etc pn non-zero in G. Okay. Therefore, what will be f set? F set can be written or f dash z divided f dash z is equal to. So now we will evaluate what will be f dash z by f z. So before that, suppose we assume that f z has one 0 z1 and one pole p1, which is a simple pole and 0 of multiplicity of 0 z1 equal to 1. Then what will happen to f dash z by f z? We will consider that first one. So before evaluating this term, if z1 is a z1 is a 0 of f z and p1 is a pole of f z, simple pole of f z. Okay. Then what will f z can be written? We will write it as, since z1 is a 0, it is z minus z1. Since p1 is a pole, it is denominator z minus p1. Okay. And into gz, where gz is non-zero. Okay. Then what will be f dash z? F dash z is equal to, we will use the quotient rule, denominator derivative of numerator. What is the numerator? Z minus z1 into gz. So in order to write the derivative of numerator, we use the product rule for differentiation. So that is first function derivative of second function plus second function derivative of first function, that is z minus z1, the derivative will be 1. Okay, whole divided by, minus numerator is z minus z1 gz, derivative of denominator, that is 1, because derivative z minus p1, derivative of z is equal to 1, whole divided by denominator square, that is z minus p1 square. So what you get, which is equal to so derivative will be by quotient rule, so which is equal to z minus p1 z minus z1 g dash z plus z minus p1 g dash z minus z minus z1 gz. Yeah, here z minus z1 g dash z plus, here gz into 1. So z minus z p1 z minus z1 g dash plus z minus p1 only g of z minus z minus z1 gz. Okay, whole divided by z minus p1 the square. Okay, so this is f dash z. Then what will be f dash z divided by f z? This is equal to z minus p1 z minus z1 g dash z. Okay, plus z minus p1 gz minus z minus z1 gz, whole divided by z minus p1 square and whole divided by fz. What is fz? Fz is equal to z minus z1 gz divided by z minus p1. So when you cancel all this term and final answer will be, so this z minus p1 for the first term, you will get z minus p1 z minus z1 g dash z whole divided by, and you can see that this square and this z minus p1 can be cancelled. So in this denominator here it is z minus p1 and now z minus z1 gz. This is the first term, and second term will be z minus p1 gz, okay, divided by this denominator z minus p1 and z minus z1 gz. Okay, and the third term minus z minus z1 gz. Okay, z minus z1 gz divided by z minus p1 z minus z1 gz. So these are the three terms when you club up all these terms. So which is equal to, cancel, this will be cancel, you get g dash z divided by gz is the first term. Okay, plus second term will be, this will be cancelled, this will be cancelled, 1 by z minus z1 minus here gz cancel, z minus z1 cancel, 1 by z minus p1. So this will be f dash z by fz. So when you have 0 z1 and 1 pole p1, it will be g dash z divided by gz plus 1 by z minus z1 minus 1 by z minus p1. z1 is a 0, p1 is the pole. suppose we have Z1 and Z2 are zeros, and P1 and P2 are poles. What will be F dash are poles? What will be F dash Z by Fz? F dash Z by Fz will be of the form G dash Z divided by Gz plus 1 by Z minus Z1 plus 1 by Z minus Z2 minus 1 by Z minus P1 minus 1 by Z minus P2. So this will be the format of F dash Z by Fz if you have zeros and poles for that function. Okay. So in generals, if there are Z1, Z2, etc., Zn are the zeros, P1, P2, etc., Pm are the poles, what will be F dash Z by Fz? So coming back to this ratio, when we have n number of zeros and m number of poles, what will be F dash Z by Fz? That will be equal to G dash Z by Gz, okay, plus 1 by Z minus Z1 plus 1 by Z minus Z2 etc. plus 1 by Z minus Zn minus 1 by Z minus P1 minus 1 by Z minus P2 etc. minus 1 by Z minus Pm. This will be the format, and that can be written G dash Z by Gz, okay, plus sigma. When you write using sigma, I can write sigma some k equal to 1 to n, okay, 1 by Z minus Zk, the summation, minus all this minus can be taken outside, so that whole minus again sigma j equal to 1 to m 1 by minus Z minus Pj. So this will be the format of F dash Z by Fz if F has Z1, Z2, etc., Zn are the zeros and P1, P2, etc., Pm are the simple poles. Okay. Now we already have G dash Z by Gz. We know Gz is non-zero, and by continuity Gz will be non-zero for a neighborhood of Z. Okay. Then G dash Z by Gz will be analytic function, right? Since G dash Z divided by Gz is analytic, and gamma is a curve in G, is a rectifiable curve in G, closed curve in G, comma, what is G? G is a region. Okay, then by Cauchy's theorem, 1 by 2 pi I integral over gamma G dash Z by Gz is 0. Okay, then by Cauchy's theorem we have G dash Z by Gz. When you have an analytic function and gamma is a simple closed curve, then integral over gamma, that analytic function will be equal to 0 by Cauchy's theorem in an open region. Right. Therefore, what will happen to F dash Z by Fz when you integrate that function? Then integral over gamma 1 by 2 pi I into integral over gamma F dash Z by Fz is of the form 1 by 2 pi I will be there here. Okay, integral over gamma G dash Z by Gz plus sigma k equal to 1 to n integral over gamma 1 by Z minus Zk dz minus sigma k j equal to 1 to m. We are integrating with respect to gamma both sides and multiply by 1 by 2 pi j equal to 1 to m integral over gamma 1 by Z minus Pj. Okay. This 1 by 2 pi is common to all these integrations. So which is equal to, we have this value is 0. So this value becomes 0. Then sigma k equal to 1 to n 1 by 2 pi I integral over gamma 1 by Z minus k dz minus sigma j equal to 1 to m 1 by 2 pi I integral over gamma 1 by Z minus Pj. So this will be the summation. So which is equal to sigma k equal to 1 to n. So what will be this? This is nothing but the definition of winding number of the point Zk with respect to the curve gamma. So which is denoted by index n gamma Zk minus sigma j equal to 1 to m. And this is again definition of index or winding number of the points Pj with respect to the curve gamma. So it is denoted by n gamma Pj. So this is 1 by 2 pi I integral over gamma f dash z divided by fz dz is of the form, we get sum of winding number of each 0 minus sum of winding number of each pole. So we can prove this theorem or argument principle in this way. Okay. So next theorem, the next result is actually subsequence or the consequence of argument principle. Which theorem says that if all the condition of argument principles are there, that means f is a meromorphic function and there are some zeros z1 etc zn and poles p1 p2 etc pm, and suppose that gamma is a closed rectifiable curve with the property that gamma is homologous to 0 and this gamma does not passes through any of these zeros and poles, and suppose we have one more condition, extra condition, if g is analytic function in g, if g is an analytic function in g, then 1 by 2 pi I integral over gamma gz into f dash z by fz can be found by using the index and poles and the function g to all the zeros and poles, that is defined by sigma j equal to 1 to n g of zj n gamma zj minus sigma 1 to m g of pj n gamma pk. Actually g of pk n gamma pk. Okay, that means g evaluated at zeros and g evaluated at poles. Then you find similarly as in the argument principle, index corresponding to each zero and index corresponding to each pole. Then you can take the sum and difference for find out this kind of integrals. Okay, how will you prove this result? It is very easy to prove by argument principle, because as in the above proof we have when fz have z1 z2 etc zn are the zeros and p1 p2 etc pm are the poles, then we have f dash z by fz is of the form what was that, sigma j equal to 1 to n 1 by z minus zj minus sigma some k equal to 1 to m 1 by z minus pk plus some, in that proof we represented this as some g dash z by g. Here we already have some analytic function g, so I represent this function as some h dash z by hz, where h is analytic and hz is non-zero. Okay, now since now let g be analytic function in g. Then you multiply this equation by this analytic function, then what will happen, gz into f dash z by fz is equal to sigma j equal to 1 to n gz divided by z minus zj minus sigma k equal to 1 to m gz divided by z minus pk plus gz h dash z divided by hz. Okay, then you multiplied by 1 by 2 pi I integrate along the curve gamma, then 1 by 2 pi I integral over gamma gz f dash z divided by fz dz is of the form which will be equal to 1 by 2 pi I integral over gamma sigma j equal to 1 to n gz divided by z minus zj minus 1 by 2 pi I integral over gamma sigma k equal to 1 to m gz divided by z minus pk plus 1 by 2 pi I integral over gamma gz h dash z divided by hz dz. And we know that h dash z by hz is analytic. In the previous proof we have g dash z by gz, the same thing is here h dash z by hz. So which is an analytic function in some neighborhood because hz is non-zero. So that gz into h dash z by hz is an analytic function in a region G and gamma is a closed rectifiable curve. Therefore again by Cauchy's theorem this integral value will become 0 by Cauchy's theorem. Okay. Therefore we have 1 by 2 pi I integral over gamma gz f dash z by fz dz is equal to, this summation can be taken outside and gz can be taken outside, therefore summation j equal to 1 to n gz integral over gamma 1 by z minus zj dz minus sigma k equal to 1 to m gz, okay, integral over gamma 1 by z minus pk dz. So what is this? This is again by definition we get sigma j equal to 1 to n. There is a mistake. This gz can't be taken outside because it includes the term variable z, right? Therefore we have to integrate this function also, which is gz, sorry. So which is equal to sigma, what will be this? Integral over gamma gz divided by z minus zj dz. It is nothing but g of zj n gamma zj, because if you take any other element z other than zj, this will be analytic, therefore integral value will become 0. When z equal to, when you replace z by zj, it is not analytic, therefore it will leads to g of zj into n gamma zj. Okay, minus here also sigma k equal to 1 to m g of, if you replace z by pk, this gz is written here inside of the integral. When you replace z by pk, this integrand is not well defined, therefore it will leads to g of pk n gamma pk. So this will be the final result. So that's about that proof.